Hi. Good afternoon, everybody. This talk will about the new features that came to Lucene 6. So the title is not really actual anymore because it was already released at the time when the talk was proposed. It was not so clear if Lucene 6 was coming out. So because of that, the title is what's coming next or what came next. So. First, about my background, I'm a Lucene committer and project management committee member of the Lucene project. I have my focus mostly on Apache Lucene, but I'm also doing Apache Solr stuff. Originally, I implemented the fast numerical search, you know, all from Solr or Elasticsearch. That you can use to do geo queries, state queries, everything. So the tree field basically was invented back in 2008 by me. I'm also love Elasticsearch, so I don't know which one to use first. So it always depends. And I'm currently working as a consultant for SD Data Solutions, which is a company in Bremen that provides support for Lucene, Solr, and Elasticsearch. So the first part of the talk will be a little bit of history. So I will not directly start with Lucene 6. I will also present you some features that came with Lucene 5. Because that's important to know when you're looking what changed in Lucene 6. So the first thing that was added in Lucene 5, which is very important for those projects that are distributed like Elasticsearch or Solr, is that we added a lot of new data safety features which made commits or replication to other computers more safe. So one of the first things that were added together with the new codec API was, for example, that all index files now have a checksum that can be verified before you're merging two segments. So if anything with the checksums doesn't match, it would not merge two index segments anymore. So the risk of losing data is reduced because of that. And in addition, those checksums can be checked on replication in Solr or Elasticsearch. That's the first thing. The second thing, which is also very important in Lucene 5, was another feature, which is a unique per segment ID. This is also important to have when you're replicating an index from one machine to another machine. You need to be sure that, for example, the other machine was creating a new index, and the new index suddenly had somehow the same segment names or something like that. And when you are replicating, it could happen that you're mixing two different indexes. And because of that, every index segment in Lucene 5 get a unique ID. So you can be sure that you're really seeing the segment you are expecting when you open the index. And as said before, this prevents bugs caused by failures in replication, like a duplicate segment file name. This is more for the thing. Then Lucene 5 was also a major step because we went already a little bit earlier to Java 7 as minimum requirement. And this is now also for data safety. So everything inside Lucene was changed to use the new Java 7 file system APIs, which have better exceptions. You can do atomic renames and all that stuff. So everything in the Lucene I/O layer was changed to use the Java 7 I/O stuff. This is something which is very funny. So nowhere in the Lucene and Solr code, no, I think in the Solr code is still there, you will find any Java I/O file or file output stream, input stream, or anything like that anymore. This is ensured by the build system of Lucene. So we can be sure that every exception we catch really describes what's gone wrong. So for example, one issue you had, if you're deleting a file and the delete fails with Java IO file, you don't get an exception, it just returns false or something like that, which leads to bugs. The other thing that was changed in Lucene 5 was that we are now using atomic renames to publish commits. So when you're looking at a Lucene 5 index or Solr 5 index, you won't see any segment scan file anymore. This file was just a helper to make the commits reliable. So that means with atomic renames, we can now instantly publish the commit of the index. We don't need to do something like renaming to a temporary file or something like that. So you can make the commit visible immediately. And the second thing we are doing now is we are also doing an fsync on the directory metadata, so that ensures that with Lucene 5, when your machine crashes directly after committing, and maybe the atomic rename was not yet persisted to disk, that you don't lose your data. So by doing an fsync, which is also only possible with Java 7, the directory metadata of your index is also available. So that makes Lucene a lot of more failure safe, especially if you have large clouds and you suddenly have crashing disks or whatever. So in that case, we also have Mike McCandless was one committer who tried that out, really. He had an index on a machine. He had something like a remote-controlled power plug, and then he was switching off while indexing the machine and rebooted it again and then checked that the index was still in a consistent state. So this is very important to have that feature. Another thing in Lucene 5 was overhaul of the codec API. You know, in Lucene 4, we started to make the indexing completely customizable, so you were able to write your own postings format. And because of that, we added a lot of new APIs during the Lucene 4 series. And because of that, at some point, the API got a little bit not nice looking anymore, and because of that, Lucene 5 changed everything. Norms also get a separate codec component. One important thing with Lucene 5 was also index merging. That changed. So the first thing is, I'm not sure if everybody has noticed that already. So when you're on Linux and you're starting Solr or Elasticsearch, it can automatically detect that your file system is running on an SSD, and because of that, it can parallelize merging of segments a bit more because you have no spinning disk, no heads moving, so you can parallelize a lot of more stuff. And so when it detects an SSD, it can improve the throughput during merging. And unfortunately, when it cannot detect that, it still assumes a spinning disk, which is the case for Windows or Macintosh platforms. But on Linux, it's automatically configured in the right way. So on the other operating systems, you have to manually change your merge scheduler to use more threads or something like that. There's also another thing that was added. It also goes in that direction. It's a merge scheduler, so it no longer in Lucene. So it automatically controls the I/O rates while indexing and merging. So previously, it could happen that you were indexing a lot of documents, and suddenly, the indexing completely stopped because the I/O system was completely saturated by the merging going on in the background. And the new merge scheduler from, I think it was from the beginning in Lucene 5, is now automatically throttling the I/O during merging. The other stuff that was done in Lucene 5 is reduced heap usage. So a lot of smaller pieces in Lucene were rewritten, so there were a lot of new bitset types added, so query filters, which are often cached, don't use so much heap space. There was also the caching wrapper filter replaced by a completely new, highly configurable filter cache, and in later versions of Lucene 5, it was also extended to queries. It also tracks the frequency of filter use, and because of that, it's much easier to include the whole thing into Apache Solr in Elasticsearch. And also merging uses much less heap. Which is also, what is also interesting, currently not visible for most users in Solr and Elasticsearch is everything in the index, reader and writers is using accountable, which allows to query the heap usage. So you get something like a nice tree view telling you how much heap every part of your index uses. Here's a segment from a Lucene 5 index. So you see the posting list is 5.2 megabytes. Okay, it's a small one. And for example, the field latitude is using 678 kilobytes. The term index, which is part of that, is using most of that memory. So this allows you to better control the heap space required by your application, because you know exactly what your index is using. You can also look at the filter cache. The filter cache also exposes that information. So every bit set tells you how much heap space it is using. Another thing that was added in Lucene 5 is custom analyzer. It was extended a little bit later. So this one is a freely configurable analyzer, which is based on the SPI framework introduced with Lucene 4 for the tokenizers. So it's similar to Apache Solr's schema XML. You have the generic names for the components, and you have more or less the same configuration options like in Apache Solr, and it's using a builder API. So this is how, from Lucene 5 on, you can build your analyzer. So it really looks like your Solr configuration. So you can choose the tokenizer, token filter. You don't need to do any subclassing. Because of that, it's much easier. So whenever I looked at code by customers creating their own analyzers, it was really horrible to look at that code, because you're repeating yourself all the time by overwriting, create components and whatever. So this one is much easier to do. The other thing that now also affects Lucene 6, so this is very important. This is the field cache is now gone in Lucene 5, and in Lucene 6 it was completely moved out of the core, I think, already. I think in 6.1 it's no longer there. It's only part of Solr, I think, because Solr still uses it for backwards compatibility. Just the information, so the field cache is what you generally call uninverting. So you have your inverted index, as you see on the right side. So you have here the list of terms in your index. And basically, in most cases, people are indexing something like a float field, having something like a boost factor or something like that. So every of those floats is, like in an inverted index, indexed as a term. It also has a term frequency and the posting list. So when you want to sort something against such an inverted index, you cannot do that easily because you only have the document ID and you want to look up the value. And because of that, you need to uninvert that. So in that case, you see that on the left side, you are creating a large array and inserting your float values for every document ID to have the random access, so you can use it for sorting. And because Lucene 4 added a new field type, which are the doc values, which is basically writing that array on the left side directly to the disk with some compression applied to it. you don't need this uninverting step anymore, so you can directly access the values from the file system via random access and use them for sorting. So the new field cache, not the new field cache, the deprecated field cache is now also using the doc values API, which was introduced by Lucene 4. And so basically, if you don't have your index upgraded yet to use doc values, you were in Lucene 5 still able to use a field cache to do sorting against some field. And this was possible because the doc values API was implemented by a new class which is called uninverting reader, which is a wrapper for your index reader. It's no longer in the core, it's in the MISC module, and this one just emulates by this uninverting that you have doc values access. Of course, this needs a lot of heap space, and because of that, you should avoid that. And also, the first query you're trying to sort against has to uninvert the index. So a lot of people know this when you started your Solr server and you don't use doc values yet, and then you start to facet. Faceting is the same issue like sorting. It takes something like 2, 3, or 4 segments, depending on your index, until the query responds, because it first has to uninvert your whole index. And because of that, doc values is the way to go. So one major change now affecting Lucene 6 came with Lucene 5.1, which is that the filter class was deprecated. So we already started to remove some of the filters in Lucene 5, and the new way to do that is just to use a simple query as the other ones and just say, I don't want to have scores for that query, because a filter is nothing more than yes or no. This document is a match or not. No, that does not affect the scoring. So we removed a lot of filters already in the early 5.1 days, which are really duplicates. So those filters were also code duplicates. They did not really bring any new special feature. So Boolean filter, this one was horrible from the beginning because it has something like ending and oring of bit sets. Terms filter is now terms query. Numeric range filter was a clone of the numeric range query, though they were deprecated and removed quite early. So basically, when you had a filtered query, now the code looks like this. So you just create a Boolean query and add your normal query clause as a must clause, and then you can add all your filters as additional filter clauses. And the filter clause just tells the Boolean query ignore the score for that. And it then returns 0 as a score, which is then added in the Boolean query to the other scores, so it does not change anymore. In Lucene 5, there's still the backwards compatibility because a lot of people were using filters, custom filters, hand-written filters, so there was some backwards compatibility. So there was the filter class still available, but it extended query, and you were able to implement the getDocID that. Now, with Lucene 6, this is no longer possible. You have to write your scorer for your own query and implement it like any other query out there. But of course, you can still use bit sets for those yes-no filter queries. So there's it's not much needed to rewrite the whole stuff. Another thing that came with Lucene 5 are two-phase iterators. All the query execution logic was split into a cheap and expensive part. The cheap part is in most cases something like, for example, in a phrase query. When you have a phrase query, the first thing you need to check is that every term in your phrase is appearing in your documents. And this is quite a cheap check because it's the same like a conjunction query. So you have a Boolean query with 3 must clauses of all your query terms, and you just have to filter everything out that does not match all those three terms. And the expensive part, which involves for phrases, for example, loading all the positions, can be done afterwards once you figure out that a query is a hit for for the matching of the three terms. And the most important thing for that is that it allows you to share common code. So previously in older Lucene versions, there was a lot of stuff, for example, from the conjunction scorer was also replicated into the phrase query scorer. So you have seen the same code everywhere. Now this allows to more easily share the code, because if you want to write a phrase query, you just need to add the position logic and can apply it afterwards. But there are also other queries which were improved by the two-phase iterators. So for example, you can use it for geographical queries. So for example, if you want to have something like a distance query where you want to find all documents in a specific distance from some point, what you can do in the easy part would be, the cheap part is just a bounding box. You just match on the bounding box, and then the more expensive part, which involves all this crazy mathematics, the hover sinus, can be done only for those which are in this bounding box to filter out all those documents which you don't want to match. This is another example where the two-phase iterators are useful. The same applied for the span queries in the 5.2 series. So span queries were almost completely rewritten. It also uses, of course, the two-phase iterators, and it shares code with the Boolean query. So if you have something like a span or query, as said before, you first have to check that is a disjunction, and afterwards you can check the positions. So this makes it possible to rewrite a lot of code. It's not yet completely done, but the first step was done in the Lucene 5.2 series. Yeah. 5.3, 4, and 5, there's not so much architectural changes anymore, so I will now come to Lucene 6, which was released, I think, in February or March approximately. I think February, yeah. So we had a lot of new features, and the first one is Lucene point values, which is, as I said in the introduction, you know, I wrote originally the numeric range query. That was in something in 2008. And the idea at that point was there were no codecs available in Lucene. So basically they were written like you would have done that at that point. So you only had a term dictionary, you had the posting lists, and because of that, it was using that features that were available. And because of the codec features, which are available since Lucene 4, the whole numeric values could be rewritten completely to use an own codec type. So it's basically no longer really using something like the inverted index. It's still based on that concept, but it's not a standard term dictionary used anymore. So this is a completely separate structure that is implemented by a codec component. And this replaces the Lucene numeric range query. The new features that you get now are, it's possible to use it in a multidimensional way. So, for example, you can index your geographic coordinates, latitudes, longitudes, or maybe also a third dimension, fourth dimension, up to 8 dimensions are possible. And this is another thing that was also, a lot of people were complaining, the numeric range query was limited to 64 bits. So you were only able to have longs or doubles as a maximum width, but you know now IPv6 is coming, and especially those people indexing their log files with IPv6 IP addresses also want to filter on those, and with numeric range query this was not possible. So with 128 bits, this is now a possibility. So you can have something like a range from an IP address to another IP address, or you can do something like this. This, I don't know the word, when you're matching on a prefix of your IP address. That's all possible now. Maybe to just explain how it works. So I wanted to explain it a little bit to you. It's not so easy to show in a presentation. So this one here is an old slide. I had something like, I think it was in 2009. This slide was in another talk. I think it was on the first Berlin Buzzwords or something like that. This explains how the numeric range queries work up to now, if you're still using the legacy numeric range queries, or in Solr it's a tree field. So basically, you have something like the terms here on the bottom of the screen. So you want to have something like match me all documents between 423 and 642. So in the earliest Lucene versions, it was something like it started in the term dictionary and went over all those terms in the lowest level, so and collected all the documents from the posting lists. Of course, with numeric values, you have a lot of distinct values in the term dictionary. So the term dictionary is huge, and you have to iterate over all those single terms to figure out which documents match them. So in the early versions, a range query was just a big OR query of all the terms between those ranges. So the idea with the numeric range queries was to add additional terms to your term index with a lower precision. And all the Solr people know it, and also Elasticsearch people. You have this special configuration value precision step in the tree field or the numeric fields. And this is exactly how many bits from your original value are clipped from the right. And now if you have something like this query, if you are indexing additional terms, instead of iterating of all those terms on the lowest level, you can simply get everything starting with 44 in one single term query. And that was the idea behind that. And the precision step was just made to give Lucene a hint how many terms should be created. So in most cases, people were using 8, which is, for an integer value, it was indexing 4 terms. So, and the new numeric fields, the point values, are using a very, very similar structure, at least for the one-dimensional case, which are block KD trees. Basically, it's for the one-dimensional case, it's basically almost the same like I have explained before. The only difference is that you don't have to give a precision step, because of using this new data structure, it can adapt automatically. So when it figures out here in this example, you see here some of those nodes have only very few terms at the end. So it does not really make sense to index all those values. So for example, in the center, you have something like 3 terms for the 6-3. So it's enough to maybe leave out some of those precisions and adapt dynamically, especially if your index is very slow. You don't need all those precisions to build the query. So with the KD trees, this is done, which is, you can read about it on Wikipedia. It's a little bit hard to explain, but there's a nice video for the two-dimensional case, which was written by which was created by Mike McCandles. Does it start? No, somehow does not want to start here. No. So unfortunately, the video does not start. Maybe it's because of the secondary screen. Let me check it. Let me change to double screen. yeah, so I think that does not really work here. Unfortunately, I did not test that. So let me go to the extended screen again. So, oops. So I skipped that. Here's a comparison between the 1D, for the 1D case, though the new point values and the numeric field. Though there's a comparison between the indexing time that was used, the query time on the left side. It was also comparing the index size and how much heap is used during searching. So first, as I said, you don't need all those precisions in your index anymore, and because of that, of course, the indexing size is also dramatically reduced. So, of course, this is not a standard index where you have all the fields in it. In that case, it was only an index using those numerical values, and because of the missing precisions, it's much more compact. There's also a speed up, of course, because there's much less disk I/O involved. So you have the query time decreases. The indexing time is also getting faster because previously the numeric fields were implemented by a separate analyzer using a special token stream, creating all those tokens. This was completely removed and is now directly in the codec level. And because of that, the indexing time is also, and during the search, the heap space is also reduced. Another thing is, so there's a comparison for the 2D case. So you see similar comparison. So for example, the classical Lucene spatial extension, which also supported the 2D case, you see, for example, the index size is much smaller in comparison to that. You also see the query time decrease, so it's a very similar picture to before. Another change in Lucene 6 is about the Java version. Lucene 6 will have a minimum requirement of Java 8. So everybody that have not yet updated to Java 8 needs to do that for Lucene and Solr 6. This is another more detailed thing is that the Lucene core char file now only uses the compact 1 profile. So theoretically, you can also run it on your mobile phone without any problems. And all the other Lucene parts using the compact 2 profile. Short note about Java 9. So Lucene 6 is completely compatible at the moment to the new Java 9 module system. So it does not use anything that tries to circumvent the security options added in Solr. So it does not do any illegal accesses to internal system classes and all that. So it works perfectly with the Java 9 module system. It also supports Unicode 8. With the ICU or the new Java 9 features. And we are currently testing Java 9 build 121. And it's still passing. So since build 116, we have it very, very stable. So you could also go into production at the moment. So it really looks good. So another change with Lucene 6 is only a default change. And this is, needs maybe some explanation. The first thing is we are changing the scoring algorithm now to use Okapi BM25, which is now the default in Lucene 6. So the question is, what's Okapi BM25? It's a bag of words retrieval function. So it does not look at positions. Basically, it's the same like TF-IDF. It's probabilistic, and it's still a function of TF and IDF. And what are the changes? So there's something TF if you have documents with some terms with a very, very high frequency. you have the problem that then the score goes up very, very unlimited, and with BM25 it's somehow bounded. So it does not go up indefinitely. So you see here in the comparison, when the term frequency goes up and up and up, you see it's still, the score goes up, but with BM25 it's limited. You can tune that a little bit. And there's also the average document length used internally, so for the whole corpus, which allows it to have something like a tuning factor to change the significance of terms internally. And the IDF of BM25 is more or less the same like TF-IDF. If you are more interested about that, I would recommend to watch the talk by Britta Weber tomorrow at the same time in Franz Club. And the other change, as noted before, is the filter class is completely gone in Lucene 6. So this one does not work anymore. You have to change to Boolean queries. All queries are now unmodifiable. The reason for that is because when you want to cache queries, you have a problem if you're using the query as a lookup key to find the cached values, and somehow this changes suddenly. So because of that, all queries are unmodifiable now. So you have, when you build a Boolean query, you have to use a builder to do that. And the query boost was removed from the query. So if you want to boost single queries, you have to now use the new boost query. The reason for that is also because it needs to be unmodifiable, so the set boost was removed. There's also a small anti-feature in Lucene 6, so it no longer has support for Lucene 4 indexes. So you need to use the index upgrader to upgrade it first to the latest Lucene 5 version. And with the coming Elasticsearch 5, it also has an automatic upgrade, so users can manually do that. How much time do I have?
3 minutes left till the end.
3 minutes. Okay. So very quickly about Solr, because there's another talk shortly after this one. The Solr 6 version has now an SQL parser included. This will be explained now in the next talk, which requires a Solr cloud backup. It's using the Presto parser, and it's using, it can be parallelized across multiple Solr nodes. It supports something like select, from, where, group by, order by, which is something like the Solr sorting, faceting, query parser. You can select the fields. So you can execute something like a query that looks like this. And you also have a JDBC driver to access that. So you just need to connect the JDBC driver to the Zookeeper host, and then you can execute the queries. So the next talk afterwards. And other feature in Solr 6 is cross-data center replication, so that allows to commit changes in one index, and this is replicated asynchronously to other data centers, so it's not instantly available on the other data center. So you don't have to wait until the data is transferred to the other data center, but of course you cannot be sure that it's immediately available on the other data center. But in most cases, this is something like you can use in between. You don't need strong replication immediately. And there are some other new features. Graph queries available. You have filters on real-time get. Doc values are returned as stored fields, and the date classes are now using the Java 8 time API. And there's the last thing I wanted to come to is the dimensional values, as described before, are unfortunately still delayed because of some problems, because of an reindex requirement. If you're still using the old tree numeric fields, you need to reindex for the upgrading, and the problem is you have to use stock values because uninverting does no longer work with the dimensional values. And for now, Solr is using the legacy numeric field as a backend for the tree field. So the classes are still available, but will go in Lucene 7. Yeah, thank you.
Thank you for... It was very short presentation by German standards, right? How many slides?
Yeah, depends on if you're counting the animations.
Okay, we are 1 minute above the time, but
okay.
Still, if we have one question, quick answer. If not, Uwe is here, just grab him during the break, ask him for coffee. Thank you very much.